Billions of invisible bullets pierce your body right now. You feel absolutely nothing. They're tiny pieces of atoms that exploded from dying stars across the galaxy. Your thick walls can't stop them. Your roof provides zero protection. Even deep underground bunkers fail completely. Tonight we're discovering why space itself shoots at Earth every second, and how this cosmic machine gun shaped every living thing on our planet. Before we dive into this invisible assault, drop a comment about where you're listening from. If you enjoy these cosmic mysteries, consider subscribing. Scientists thought they understood radioactive energy completely. Radioactive energy means invisible rays that can damage living things. All this dangerous energy came from rocks in the ground. The higher you climbed from Earth, the safer you became. Victor Hess strapped a radiation detector to a balloon in 1912. A radiation detector measures invisible dangerous rays. He climbed toward the stratosphere to test this obvious fact. His instruments recorded something impossible. Radiation levels increased with altitude. At 16,000 feet above ground, he measured 3 times more deadly rays than at sea level. The universe was bombarding our planet with invisible atomic bullets. Space itself was shooting radioactive particles at Earth. We had been living under cosmic gunfire without knowing it. This discovery earned Hess a Nobel Prize and changed physics forever. For the first time, humans realized that deadly atomic projectiles rain down from space constantly. Right now, cosmic projectiles hit every square inch of your skin. About 100 tiny atomic pieces pierce through you every single second. These are called cosmic rays, high-energy particles from space. Your house can't protect you from cosmic rays. Concrete walls slow these particles slightly but cannot stop them. Steel beams provide no meaningful barrier. Even thick lead shielding barely reduces the bombardment. These cosmic bullets carry enormous energy. They traveled millions of light years through space before reaching Earth. Most maintain speeds approaching light speed when they hit your body. Your genetic material takes 15,000 cosmic hits per year. Each impact packs enough energy to break the chemical bonds that hold your DNA together. Evolution adapted to this constant atomic bombardment over billions of years. This invisible assault affects every living thing equally. The cosmic ray democracy ensures that rich and poor, young and old, all receive identical doses from space. Some cosmic rays carry energy levels that stagger the imagination. Earth's most powerful particle accelerator creates high-energy atomic bullets for scientific research. But cosmic rays from space make our best machines look pathetic. The most extreme cosmic rays carry 1,000,000 times more energy than anything humans can create. These ultra-high energy particles race through the universe with incredible power. They represent nature's ultimate particle accelerator at work. Scientists call these the most energetic particles in the universe. When they finally reach Earth after traveling billions of miles, they still carry enough energy to light up an entire city block. These cosmic monsters arrive so rarely that detecting one feels like winning the cosmic lottery. Only a few dozen hit Earth's entire atmosphere each year. Each one carries the kinetic energy of a baseball thrown at 100 miles per hour, all packed into a single atomic particle. The universe operates particle accelerators far more powerful than anything humans have ever built or imagined. Cosmic rays arrive at Earth from every possible direction. They come from the left, right, up, down, and everywhere in between. This creates one of the most democratic phenomena in the universe. Scientists expected cosmic rays to come mainly from one direction, perhaps from the center of our galaxy where most stars live, or maybe from the direction of our solar system's motion through space. The measurements revealed something completely different. Cosmic rays arrive almost uniformly from all directions across the sky. The cosmic bombardment shows no favoritism for any particular region of space. This uniform arrival pattern tells us something profound about the universe. The cosmic ray sources must be scattered throughout the galaxy and beyond. Space itself is filled with cosmic accelerators shooting particles in every direction. Whether you live in New York or Tokyo, the cosmic ray dose remains virtually identical. The universe practices perfect equality in its invisible atomic warfare. Cosmic rays travel at speeds that challenge human comprehension. Most cosmic particles race through space at more than 90% of light speed. Light speed represents the ultimate cosmic speed limit. These particles began their journey from exploding stars, massive black holes, or other cosmic catastrophes. They've been racing through empty space for millions or billions of years without slowing down. When cosmic rays finally reach Earth's atmosphere, they still maintain these incredible speeds. Nothing in space can slow them down significantly. The cosmic vacuum provides no friction or resistance to their motion. At these extreme velocities, cosmic rays experience the strange effects that Einstein predicted. Time passes more slowly for the particles themselves. Distance becomes compressed in their reference frame. For cosmic rays, the journey across our entire galaxy takes much less time than we would measure. They exist in a relativistic world where the normal rules of time and space become twisted by their incredible speed. Cosmic rays possess penetrating power that mocks human attempts at protection. The thickest lead shields that stop medical X-rays barely slow down cosmic particles. These atomic bullets punch through matter as if it were tissue paper. Underground bunkers provide some protection, but cosmic rays still find their way inside. Rock, concrete, steel, and water all fail to provide complete shielding. The particles simply punch through everything in their path. Some cosmic rays can penetrate miles of solid rock. They travel through entire mountains and emerge on the other side with most of their energy intact. Even the deepest mines on Earth cannot escape cosmic ray bombardment completely. This incredible penetrating power comes from the particles' enormous energy and tiny size. Cosmic rays consist of individual atomic nuclei or electrons. They're much smaller than the atoms they encounter in shielding materials. The universe has created the perfect armor-piercing ammunition in cosmic rays. No human technology can provide complete protection from this invisible space artillery. Cosmic rays don't travel in straights across the galaxy. Massive magnetic fields in space act like cosmic bumpers, constantly deflecting charged particles. This creates a galaxy-sized pinball machine with cosmic rays as the balls. Our galaxy contains magnetic fields stretched across thousands of light years. When electrically charged cosmic ray particles encounter these fields, they get deflected onto curved paths. The particles bounce from field to field like pinballs. This magnetic deflection explains why cosmic rays arrive at Earth from all directions. The particles began their journey from specific sources, but magnetic fields scattered them throughout the galaxy during their long voyage. The magnetic pinball effect also traps many cosmic rays inside our galaxy for millions of years. They bounce around between magnetic field regions, slowly working their way toward the edge of the galactic disk. Without these galactic magnetic fields, cosmic rays would travel in straight lines from their sources. We could point telescopes at cosmic ray arrival directions and identify exactly where they originated. When a high-energy cosmic ray finally hits Earth's atmosphere, it triggers an invisible atomic crash. The cosmic particle slams into an air molecule 60 miles above your head. This collision creates an explosion of secondary particles. The original cosmic ray shatters into dozens of new particles during the atmospheric collision. These secondary particles race downward and collide with more air molecules. Each collision creates even more particles in a growing cascade. This process is called an air shower. A single cosmic ray can create billions of secondary particles before reaching ground level. The invisible particle shower spreads across several square miles of Earth's surface. Most cosmic ray detectors on Earth actually detect these secondary particles, not the original cosmic rays themselves. The primary cosmic bullets get destroyed in the upper atmosphere during their first collision with air. By the time the particle shower reaches you, it contains mostly muons and electrons. Muons are heavy cousins of electrons that can penetrate deep underground. These are the cosmic ray particles that actually pass through your body. Earth possesses a magnetic shield called the magnetosphere. This invisible magnetic bubble surrounds our entire planet. It provides partial protection against the weakest cosmic rays, deflecting low-energy particles before they reach our atmosphere. The magnetosphere works like a cosmic force field. Electrically charged particles from space get caught in Earth's magnetic field lines. Instead of hitting our atmosphere directly, weak cosmic rays get deflected around the planet. This magnetic protection works best at Earth's equator and becomes weaker near the North and South poles. Cosmic ray intensity increases as you travel toward the polar regions where Earth's magnetic field lines point straight down. However, the most energetic cosmic rays punch right through Earth's magnetic shield. The magnetosphere can only deflect relatively low-energy particles. Ultra-high-energy cosmic rays ignore our magnetic protection completely. Without this magnetic shield, Earth would receive much higher doses of cosmic radiation. The magnetosphere represents one of the key factors that makes life on Earth possible. Our Sun creates a cosmic traffic control system that regulates cosmic ray flow. The solar wind consists of charged particles streaming outward from the Sun at millions of miles per hour. This creates a bubble around our solar system. During periods of high solar activity, the solar wind becomes stronger. This enhanced solar wind pushes against incoming cosmic rays, reducing the number that reach Earth. Solar storms actually decrease cosmic ray levels temporarily. The Sun follows an 11-year activity cycle. During solar maximum, cosmic ray levels drop to their lowest values. During solar minimum, cosmic rays reach peak intensity at Earth. The Sun and cosmic rays play a cosmic tug-of-war. This solar modulation affects mainly lower-energy cosmic rays. The most powerful cosmic particles ignore the solar wind completely and maintain constant intensity regardless of solar activity. Astronauts traveling beyond Earth's magnetic field must worry about both solar radiation and cosmic rays. During solar storms, solar particle radiation becomes the immediate danger, while cosmic rays provide the constant background threat. Cosmic rays create a biological paradox. They damage DNA and cause mutations that can lead to cancer and genetic diseases. Yet this same cosmic bombardment has driven evolution and biodiversity throughout Earth's history. Every living thing on Earth receives a constant dose of cosmic radiation. This background radiation breaks chemical bonds in DNA molecules, creating genetic mutations in all organisms. Most mutations are harmful or neutral, but a few provide evolutionary advantages. Without cosmic ray mutagenesis, evolution would proceed much more slowly. The cosmic particle bombardment provides a constant source of genetic variation that natural selection can act upon. Life has adapted to this radiation environment over billions of years. Scientists estimate that cosmic rays contribute to roughly 10% of the natural background radiation that affects human health. This cosmic dose remains relatively constant throughout human lifetimes, unlike medical X-rays or nuclear accidents. The universe has been running a 4-billion-year genetic engineering experiment on Earth using cosmic ray radiation. This invisible bombardment helped create the incredible diversity of life we see today. What exactly are these cosmic bullets that pierce through your body? Most people imagine exotic alien particles from distant galaxies. The reality proves far more ordinary and far more profound. Cosmic rays consist mostly of protons. Protons are the centers of hydrogen atoms, the simplest and most common atoms in the universe. About 90% of all cosmic ray particles are these basic hydrogen nuclei. These protons lost their electrons somewhere during their violent journey through space. An atom without its electrons becomes just a bare nucleus. This naked proton carries a positive electric charge as it races through the cosmos. The universe built its cosmic artillery from the most basic building blocks possible. Hydrogen makes up most of normal matter everywhere. Stars burn hydrogen as fuel. Gas clouds between stars contain mostly hydrogen. This cosmic ray composition reflects the universe's fundamental chemical makeup. The most abundant element in space becomes the most common cosmic projectile aimed at Earth. The second most common cosmic ray particles are alpha particles. Alpha particles are helium nuclei, the centers of helium atoms with both electrons stripped away. These heavier cosmic bullets make up about 9% of the cosmic bombardment. Each alpha particle contains 2 protons and 2 neutrons bound tightly together. This makes them 4 times heavier than hydrogen nuclei, but incredibly stable. Alpha particles can survive million-year journeys through space without falling apart. Helium ranks as the second most abundant element in the universe. Stars create helium by fusing hydrogen atoms together in their cores. When massive stars explode, they scatter both hydrogen and helium throughout space. These alpha particles carry more momentum than protons because of their greater mass. When they hit Earth's atmosphere, they create bigger particle showers. Each alpha particle packs more punch than individual protons. The cosmic ray recipe mirrors the universe's stellar cooking. The same nuclear fusion processes that power also determine what gets shot at Earth from space. Less than 1% of cosmic rays consist of heavy elements. Heavy elements mean anything more complex than helium: carbon, oxygen, silicon, iron, and dozens of others. This tiny fraction carries enormous scientific value. These heavy atomic nuclei provide a cosmic archaeology project. Each heavy element tells the story of where it was forged. Carbon and oxygen come from medium-sized stars. Silicon and iron require massive stellar explosions to create. The heavy element cosmic rays reveal which types of stars contributed to the cosmic particle population. Scientists can identify cosmic ray sources by analyzing the mix of elements. Different stellar environments produce different element ratios. On Earth, heavy elements make up a significant portion of rocky planets and living organisms. But in cosmic rays, they represent rare exotic species. The cosmic bombardment remains dominated by simple hydrogen and helium. This compositional difference reveals that cosmic ray sources favor environments where light elements dominate. Gas clouds, stellar winds, and supernova shocks all contain mostly hydrogen and helium. Some cosmic rays consist of antimatter particles. Antimatter represents the mirror opposite of normal matter. The most common antimatter cosmic rays are positrons, particles identical to electrons but with opposite electric charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. This makes antimatter extremely rare in our normal matter universe. Yet cosmic ray detectors regularly find antimatter particles arriving from space. These antimatter cosmic rays tell scientists about exotic physics processes occurring throughout the galaxy. Certain types of particle interactions can create antimatter. Black holes, pulsars, and cosmic ray collisions all produce antimatter particles. The antimatter cosmic rays arrive in tiny quantities compared to normal matter particles. For every 1,000 protons, only one positron reaches Earth. But this small population provides big clues about high-energy physics in space. Finding antimatter in cosmic rays proves that the universe operates natural particle accelerators far more powerful than anything humans have built. The cosmos routinely creates conditions too extreme for Earth-based laboratories. Cosmic ray particles carry isotope signatures that reveal their origins. Isotopes are different versions of the same element with varying numbers of neutrons. Each stellar environment creates distinctive isotope ratios like cosmic fingerprints. The isotope ratios in cosmic rays differ significantly from those found in our solar system. This proves that cosmic rays didn't originate from our local stellar neighborhood. They traveled here from distant parts of the galaxy with different stellar histories. Scientists can identify specific types of stellar explosions by examining cosmic ray isotopes. Supernovas, nova explosions, and stellar winds each produce characteristic isotope patterns. The cosmic ray isotope mix reveals which processes dominate cosmic ray acceleration. Some rare isotopes in cosmic rays have extremely short lifetimes. These unstable isotopes decay within millions of years. Finding them in cosmic rays proves that at least some cosmic particles began their journey recently from nearby sources. The isotope evidence shows that cosmic rays sample material from throughout our galaxy's history. Ancient stellar generations and recent stellar explosions both contribute to the cosmic particle bombardment hitting Earth. Cosmic ray energy follows a strict hierarchy that spans enormous ranges. Low-energy cosmic rays vastly outnumber high-energy ones. For every cosmic ray that carries extreme energy, billions arrive with modest power. This energy distribution follows what scientists call a power law. When cosmic ray energy increases by a factor of 10, the number of particles decreases by a factor of 1,000. High-energy cosmic rays become exponentially rarer. Most cosmic rays hitting your body carry relatively low energies. These common low-energy particles can barely penetrate through a sheet of paper if they weren't moving so fast. Their high speed gives them penetrating power despite modest energy. The rare high-energy cosmic rays carry millions of times more energy than typical particles. These cosmic monsters can punch through entire mountains, but you might wait years before one of these ultra-high energy particles hits your location. This energy spectrum reveals that the universe operates many different types of cosmic accelerators. Weak acceleration processes create numerous low-energy particles. Extreme acceleration environments produce few high-energy monsters. Every cosmic ray particle arrives at Earth as a completely naked atomic nucleus. Naked nucleus means an atomic core with all its electrons stripped away. The violent cosmic environment removes every electron from every atom. Normal atoms on Earth remain clothed with electron clouds surrounding their nuclei. These electrons give atoms their chemical properties and allow them to form molecules. cosmic ray nuclei have none of these electron companions. The stripping process occurs during the cosmic ray's violent birth and journey through space. High-energy collisions, magnetic fields, and radiation all work to remove electrons from atoms. Space provides no gentle environment for preserving electron clouds. When these naked nuclei finally hit Earth's atmosphere, they immediately begin collecting electrons from air molecules. The cosmic particles try to rebuild their electron clouds during the final microseconds before collision. This universal nakedness proves that cosmic rays experienced extreme conditions somewhere during their cosmic voyage. The gentle environments of planetary surfaces never produce such completely ionized matter. The cosmic ray element census reveals a clear pattern of lightweight domination. Hydrogen and helium make up 99% of all cosmic ray particles. But the remaining 1% spans the entire periodic table from lithium to uranium. This elemental mix matches the general composition of the universe with some important differences. The universe contains mostly hydrogen and helium everywhere. Stars, gas clouds, and even planets reflect this basic cosmic recipe. However, cosmic rays show slight enrichment in certain heavy elements compared to typical cosmic abundances. Elements like carbon, oxygen, and iron appear more frequently in cosmic rays than expected. This enrichment provides clues about cosmic ray sources. The heaviest elements in cosmic rays include iron, nickel, and even uranium nuclei. These rare heavy cosmic bullets pack enormous destructive power when they hit Earth's atmosphere. A single uranium cosmic ray can create a particle shower spanning several miles. The complete elemental spectrum in cosmic rays demonstrates that the universe accelerates particles from every type of stellar environment. From hydrogen gas clouds to iron-rich supernova remnants, all contribute to the cosmic bombardment. During their million-year journey through space, cosmic ray particles crash into thin gas between stars. These cosmic crashes break apart heavy atomic nuclei like cosmic car accidents. The collision fragments create lighter elements that weren't present originally. This fragmentation process explains why cosmic rays contain unusual amounts of lithium, beryllium, and boron. These light elements rarely form in stars, but appear frequently in cosmic rays. Space collisions manufacture them from heavier nuclei. When a carbon nucleus hits an interstellar hydrogen atom, the collision can shatter the carbon into smaller pieces. Boron, beryllium, and lithium nuclei result from these cosmic crack-ups. The fragments continue racing through space as secondary cosmic rays. Scientists use these fragmentation products as cosmic odometers. The more light elements present in cosmic rays, the more collisions occurred during their journey. This reveals how much material cosmic rays encountered traveling from their sources to Earth. The fragmentation signature proves that most cosmic rays traveled vast distances through space before reaching us. Local cosmic ray sources would show less fragmentation damage. The cosmic bombardment comes mainly from distant parts of our galaxy. Space operates a giant nuclear laboratory that creates elements impossible to forge in stellar cores. When cosmic ray nuclei collide with interstellar gas, the crashes produce nuclear reactions that synthesize new elements through a process called spallation. Spallation reactions work like atomic demolition projects. High-energy cosmic ray nuclei smash into gas atoms and break both participants into smaller fragments. These fragments can combine in ways that stellar nuclear furnaces cannot achieve. This cosmic nuclear alchemy produces lithium, beryllium, and boron in space. Stars destroy these fragile elements rather than create them. Only the violent cosmic ray collision environment can manufacture and preserve these light elements. The spallation process also creates radioactive isotopes with short lifetimes. Some of these unstable nuclei decay within thousands of years. Finding them in cosmic rays proves that spallation reactions continue actively throughout the galaxy. Cosmic rays essentially perform billions of nuclear physics experiments every second throughout space. The universe runs a vast particle accelerator laboratory that spans entire galaxies and operates continuously for billions of years. Stars don't die quietly. When massive stars exhaust their nuclear fuel, they explode in catastrophic events called supernovas. These stellar explosions create shock waves that race outward at thousands of miles per second through space. Supernova remnants become cosmic particle accelerators more powerful than anything humans have ever built. The explosion shock wave slams into surrounding gas clouds and magnetic fields. This collision accelerates nearby particles to incredible energies over thousands of years. A single supernova explosion can continue accelerating cosmic ray particles for 100,000 years after the star dies. The expanding shock wave maintains its particle accelerating power across vast regions of space. These stellar graveyards become cosmic ray factories spanning dozens of light years. Most cosmic rays hitting Earth began their journey at supernova remnant acceleration sites. The violent stellar explosion environment provides the extreme conditions needed to boost particles to cosmic ray energies. The universe operates thousands of these stellar explosion factories throughout our galaxy. Each dying massive star contributes to the cosmic particle bombardment that eventually reaches Earth. How do supernova shock waves actually accelerate particles to such extreme energies? The process works like a cosmic pinball machine with magnetic fields as the bumpers. Scientists call this mechanism Fermi acceleration after the physicist who first explained it. Charged particles bounce back and forth across the supernova shockwave boundary. Each bounce increases the particle's energy slightly. Magnetic field irregularities on both sides of the shock act like cosmic ping-pong paddles batting the particles around. The particle gains energy every time it crosses the shock wave in either direction. This happens because the shock front moves at high speed. Particles bouncing off a moving surface gain extra energy with each collision. After millions of bounces across the shock boundary, particles accumulate enormous energies. The ping-pong acceleration process can boost protons to energies millions of times higher than they started with. This magnetic pinball mechanism explains how relatively simple stellar explosions create the most energetic particles in the universe through repeated acceleration cycles. Multiple massive stars often live and die in the same region of space. When several supernovas explode near each other, they create enormous hot bubbles called superbubbles. These cosmic pressure cookers provide ideal environments for long-term particle acceleration. Superbubbles can stretch across hundreds of light years of space. The hot gas inside reaches temperatures of millions of degrees. Multiple shock waves from different supernova explosions interact and strengthen each other within these bubbles. Particles trapped inside superbubbles experience repeated acceleration from multiple shock waves. The complex magnetic field structure keeps cosmic rays bouncing around for millions of years. This extended acceleration time allows particles to reach even higher energies. Our solar system currently sits inside a superbubble created by ancient stellar explosions. This local hot bubble affects the cosmic ray population reaching Earth. The bubble's magnetic fields partially deflect lower energy cosmic rays from other parts of the galaxy. These giant cosmic bubbles demonstrate how stellar neighborhoods collaborate to create enhanced particle acceleration regions throughout the galaxy. Some dead stars refuse to stay quiet. Pulsars are rapidly spinning neutron stars with incredibly strong magnetic fields. A neutron star contains the mass of our Sun compressed in a city-sized sphere, spinning hundreds of times per second. Young pulsars accelerate particles through their powerful rotating magnetic fields. The spinning magnetic field creates electric fields that can accelerate particles to nearly light speed. These cosmic dynamos act like enormous electromagnetic slingshots. Particles gain energy as they spiral outward along the pulsar's magnetic field lines. The acceleration continues until particles reach the light cylinder, a boundary where the magnetic field can no longer contain them. At this point, particles escape as high-energy cosmic rays. The most energetic cosmic ray acceleration occurs near pulsars less than 10,000 years old. These young spinning dynamos haven't yet slowed down enough to lose their particle accelerating power. They represent some of the most efficient cosmic ray factories in the galaxy. The pulsar acceleration mechanism creates cosmic ray beams that sweep across space like lighthouse beams as the neutron star rotates. The centers of some galaxies harbor supermassive black holes millions of times heavier than our Sun. These cosmic monsters don't just swallow matter. They also launch high-speed jets of particles across millions of light-years of space. Active galactic nuclei create these jets through processes that scientists still don't fully understand. Matter falling into the black hole somehow gets redirected into narrow beams, moving at nearly light speed. These jets carry enormous of energy away from the black hole. The jet particles travel at relativistic speeds, meaning speeds close enough to light speed that Einstein's relativity effects become important. When these ultra-high-speed particles finally slow down, they become some of the most energetic cosmic rays in the universe. These galactic jet engines can remain active for millions of years. They spray high-energy particles across vast distances, seeding multiple galaxies with cosmic rays. Some jets extend so far that they dwarf entire galaxies in length. The most powerful cosmic rays detected on Earth likely originated from these supermassive black hole particle cannons in distant galaxy centers. Gamma-ray bursts represent the most violent explosions in the universe since the Big Bang. These catastrophic events release more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. They occur when the most massive stars collapse into black holes. The extreme conditions during gamma-ray bursts may create the highest energy cosmic rays ever detected. The explosion generates magnetic fields and particle accelerations beyond anything else in the universe. These cosmic cataclysms push physics to its absolute limits. Ultra-high-energy cosmic rays with energies approaching the theoretical maximum possible may originate from gamma-ray burst explosions. These particles carry so much energy that they interact with cosmic background radiation during their journey through space. Gamma-ray bursts happen relatively rarely. Only a few occur in our galaxy every million years, but when they do occur, they likely flood nearby regions of space with extremely energetic cosmic ray particles for thousands of years afterward. These ultimate cosmic explosions may explain why astronomers detect cosmic ray particles with energies that seem impossible to create through normal stellar processes. Some galaxies produce new stars at incredible rates. Starburst galaxies create stars hundreds of times faster than our Milky Way. This rapid stellar birth rate also means rapid stellar death rates as massive stars quickly burn out and explode. The concentrated supernova activity in starburst galaxies creates cosmic ray production lines. Dozens or hundreds of stellar explosions occur within relatively small galactic regions over short time periods. This creates enhanced cosmic ray acceleration environments. Starburst galaxies become cosmic ray powerhouses that can influence neighboring galaxies. The intense cosmic ray production creates galactic winds that carry high-energy particles far beyond the original galaxy boundaries. These galactic outflows seed intergalactic space with cosmic rays. Astronomers can detect the enhanced cosmic ray activity in starburst galaxies through their intense radio and gamma ray emissions. The cosmic ray particles interact with magnetic fields and gas to produce these detectable radiation signatures. These stellar baby boom regions demonstrate how galaxy-scale star formation processes can dominate cosmic ray production across vast regions of the universe. The detailed physics of how shockwaves accelerate particles involves complex plasma instabilities. Plasma is a state of matter where atoms are broken apart into free electrons and nuclei. Most matter in space exists in this plasma state. When fast-moving plasma meets slower plasma at a shockwave boundary, the collision creates magnetic field turbulence. These plasma instabilities act like cosmic surfboards that particles can ride to higher energies. The turbulent magnetic fields repeatedly kick particles to higher speeds. Diffusive shock acceleration allows particles to gain energy through multiple encounters with the turbulent shockwave region. Particles randomly walk back and forth across the shock boundary, gaining energy with each crossing. This stochastic process gradually builds up enormous particle energies. The plasma instability mechanism explains why shockwave acceleration works so efficiently throughout the universe. Nearly every high-speed collision in space creates the plasma conditions needed for particle acceleration. This fundamental plasma physics process operates at shockwaves ranging from solar wind interactions to galaxy cluster collisions, making it the universe's most common cosmic ray acceleration mechanism. Magnetic fields in space sometimes become tangled and twisted like rubber bands under tension. When these twisted magnetic field lines suddenly snap and reconnect in simpler configurations, the stored magnetic energy gets released explosively. This process is called magnetic reconnection. Magnetic reconnection events accelerate particles by converting magnetic field energy directly into particle kinetic energy. The reconnection process creates electric fields that can boost particles to high speeds almost instantaneously. This differs from the gradual acceleration of shockwave mechanisms. Solar flares represent familiar examples of magnetic reconnection in action. The sun's twisted magnetic field lines snap and reconnect explosively, releasing enormous amounts of energy and accelerating particles throughout the solar system. Magnetic reconnection occurs throughout the universe wherever twisted magnetic fields exist. Pulsar magnetospheres, stellar coronas, and galactic magnetic fields all experience reconnection events that contribute to cosmic ray acceleration. This magnetic energy conversion mechanism provides an efficient way to transform the universe's abundant magnetic field energy into high-energy cosmic ray particles. Galaxy clusters represent the largest gravitationally bound structures in the universe. When these massive collections of galaxies collide and merge, they create shock waves that span millions of light years. These represent the largest particle accelerators in the universe. Galaxy cluster mergers generate shock waves moving at thousands of miles per second through the thin gas between galaxies. These enormous shocks can accelerate particles across regions larger than entire galaxies. The acceleration process continues for hundreds of millions of years. The coma cluster collision created shock waves, still accelerating cosmic ray particles today, long after the initial galaxy collision occurred. Radio telescopes can detect the cosmic ray electrons accelerated by these ancient cluster merger shock waves. Galaxy cluster shocks may contribute significantly to the cosmic ray population in intergalactic space. These universe-spanning accelerators process enormous amounts of material and can boost particles to very high energies through extended acceleration times. The largest structures in the universe thus operate as the largest particle accelerators, demonstrating cosmic ray acceleration on the grandest possible scales. Wolf-Rayet stars are among the most massive and luminous stars in the universe. These stellar giants burn their nuclear fuel so rapidly that they blow away their outer layers in powerful stellar winds. The wind speeds reach thousands of miles per second. When Wolf-Rayet stellar winds collide with surrounding gas clouds, they create collision zones that accelerate cosmic ray particles. These wind-blown bubbles act like stellar-scale supernova remnants, generating shock waves and magnetic turbulence ideal for particle acceleration. The collision between stellar wind and interstellar gas creates bow-shock structures similar to those formed by supersonic aircraft. These stellar bow shocks can accelerate particles to cosmic ray energies over the star's lifetime. Multiple Wolf-Rayet stars in stellar associations create overlapping wind collision zones that enhance particle acceleration. These stellar wind interaction regions can span dozens of light years and operate for millions of years. Massive stars thus create cosmic ray acceleration sites even before they die in supernova explosions, contributing to galactic cosmic ray production throughout their active lifetimes. Our Sun usually produces relatively gentle solar wind particles that pose little threat to Earth. But occasionally, the Sun becomes a cosmic ray accelerator through violent solar flares and coronal mass ejections. These solar explosions can boost particles to dangerous energies. Solar energetic particle events occur when magnetic field lines in the Sun's corona snap and reconnect explosively. The magnetic energy release accelerates protons and electrons to speeds approaching 10% of light speed within minutes. Major solar particle events can create radiation doses dangerous to astronauts and airline passengers. The most powerful solar cosmic ray events can disrupt satellite electronics and create communication blackouts on Earth's daylight side. Solar cosmic rays represent the only cosmic particle source close enough for detailed study. Scientists use spacecraft and ground-based detectors to monitor solar particle acceleration in real time as events unfold. While solar cosmic rays are much less energetic than galactic cosmic rays, they demonstrate that cosmic ray acceleration processes operate even in our relatively quiet stellar neighborhood. Cosmic ray energies follow one of the most rigid laws in the universe. This energy distribution creates a cosmic hierarchy more strict than any human society. The rule is simple but brutal. For every factor of 10 increase in energy, the number of particles decreases by a factor of 1,000. Scientists call this pattern a power law distribution. Power law means that small changes in energy create enormous changes in particle numbers. Low-energy cosmic rays vastly outnumber high-energy ones by incredible ratios. When cosmic ray energy increases by 10 times, particle numbers drop by 1,000 times. This mathematical relationship holds across the entire energy range, from the weakest cosmic rays to the most powerful ones ever detected. The power law creates a cosmic democracy of energy, where common particles carry modest power, while rare particles carry devastating energy. This energy hierarchy spans more than 10 orders of magnitude. a range larger than the difference between an ant and an elephant. This mathematical rule reveals that the universe operates cosmic ray acceleration processes that naturally create this extreme energy distribution across all galactic environments. At a specific energy level, the cosmic ray energy distribution suddenly changes behavior. This energy level sits around 10 to the 15th power electron volts. Scientists call this feature the knee because the energy spectrum bends like a human knee joint. Below the knee, cosmic ray numbers drop moderately as energy increases. Above the knee, particle numbers plummet much more rapidly. The cosmic energy highway takes a sharp turn at this critical energy threshold. The knee represents the energy limit where our galaxy's cosmic ray accelerators begin to run out of power. Supernova remnants and other galactic sources cannot efficiently boost particles beyond knee energies. This creates the sudden change in the energy distribution slope. The knee energy corresponds to about 3 million times the energy that Earth's most powerful particle accelerators can achieve. Yet this represents just the beginning of cosmic ray energy extremes. Even more exotic features exist at higher energies. This cosmic energy landmark divides the galactic cosmic ray population from more exotic extragalactic sources that dominate higher energies. Something unexpected happens at cosmic ray energies around 10 to the 18th power electron volts. The steep energy decline that began at the knee suddenly becomes much gentler. Scientists call this feature the ankle because the energy spectrum resembles a human ankle joint. The ankle creates a cosmic energy plateau where particle numbers stop dropping so rapidly. This suggests that a new type of cosmic ray source begins contributing significantly at ankle energies. The ankle represents a transition zone between different cosmic ray populations. Most scientists believe the ankle marks the energy where extragalactic cosmic rays begin to dominate over galactic ones. Cosmic ray sources outside our galaxy start contributing more particles than sources within the Milky Way at these extreme energies. The ankle energies correspond to about 100 million times the energy achievable by human particle accelerators. These cosmic ray particles carry energy equivalent to a baseball moving at highway speeds, all contained within a single atomic nucleus. This ankle transition reveals that the universe operates at least two distinct cosmic ray acceleration systems, one galactic and one extragalactic. The most energetic cosmic ray particles face an unexpected obstacle during their journey through space. The universe itself contains a faint background glow left over from the Big Bang. This cosmic background radiation creates an energy ceiling for the highest energy cosmic rays. When ultra-high energy cosmic ray particles interact with background radiation photons, they lose energy through particle creation reactions. This process is called the GZK cutoff after the scientists who predicted it. GZK stands for Greason, Zatsepin, and Kozmin. The GZK cutoff creates a cosmic energy speed trap that prevents particles from traveling long distances while maintaining extremely high energies. Cosmic rays above the cutoff energy cannot reach Earth from distant galaxy clusters without losing significant energy. This background radiation interaction limits ultra-high energy cosmic ray sources to relatively nearby regions of the universe. The most powerful cosmic ray particles detected on Earth must have originated within about 100 million light-years of our galaxy. The universe thus enforces its own cosmic speed limits through fundamental physics interactions that operate throughout all of space. A cosmic transition occurs at energies above the knee where galactic cosmic ray sources begin losing their dominance. Sources within our Milky Way galaxy cannot efficiently accelerate particles beyond certain energy limits. Extragalactic sources gradually take control of the cosmic ray population. This transition happens gradually over several orders of magnitude in energy. Below the knee, galactic supernova remnants and other local sources provide most cosmic ray particles. Above the ankle, extragalactic sources dominate completely. This galactic to extragalactic transition explains why cosmic ray composition changes with energy. Galactic sources accelerate mainly light elements like hydrogen and helium. Extragalactic sources appear to accelerate more heavy elements from different stellar environments. This changing of the cosmic guard occurs because different acceleration mechanisms have different maximum energy capabilities. Local galactic shockwaves reach their limits while distant galaxy clusters and active galactic nuclei continue accelerating particles to higher energies. The cosmic ray energy spectrum thus maps the relative influence of different cosmic acceleration processes operating across various scales throughout the universe. Beyond 10 to the 20th power electron volts, cosmic ray particles become so rare that detecting one feels like winning the cosmic lottery. These ultra-high energy events occur at Earth only about once per square kilometer per century. The entire planet receives roughly one such particle per year. Each ultra-high energy cosmic ray carries the kinetic energy of a tennis ball served by a professional player, all packed into a single atomic nucleus. These represent the most energetic particles ever detected in the universe. Their rarity makes them among the most precious scientific data in existence. The extreme rarity of these cosmic monsters means that scientists must build enormous detector arrays covering thousands of square kilometers to catch even a few events per year. Each detection provides crucial information about the universe's most powerful acceleration mechanisms. Ultra-high energy cosmic rays arrive so infrequently that some detectors operate for years between significant events. When one finally hits, it triggers instrument responses across areas the size of entire cities as the particle creates a massive atmospheric shower. This cosmic rarity demonstrates that the universe operates particle accelerators so powerful and so distant that their products barely reach Earth despite traveling for millions of years. As cosmic ray energy increases, the mix of elements changes dramatically. Low-energy cosmic rays consist mostly of light elements like hydrogen and helium. High-energy cosmic rays contain increasing proportions of heavy elements like iron and nickel. This composition change provides crucial clues about different cosmic ray source types. Light element dominance at low energies reflects acceleration by galactic supernova remnants in hydrogen-rich environments. Heavy element enhancement at high energies suggests acceleration by more exotic sources. The composition evolution happens gradually across the energy spectrum. Scientists can trace the transition by analyzing the secondary particle showers created when cosmic rays hit Earth's atmosphere. Heavy nuclei create different shower signatures than light nuclei. Different elements also reach different maximum energies before galactic magnetic fields can no longer contain them. Iron nuclei can reach higher energies than protons in the same acceleration environment because their electric charge allows stronger magnetic confinement. This cosmic chemical evolution reveals how different stellar environments throughout the universe contribute to the cosmic ray population at different energy levels. Our Sun operates a cosmic traffic control system that regulates which cosmic rays can reach Earth. The solar wind creates a magnetic bubble around our solar system that varies in strength over an 11-year cycle. This solar cycle creates predictable changes in cosmic ray intensity. When solar activity increases during solar maximum, the enhanced solar wind blocks more low-energy cosmic rays from entering our solar system. When solar activity decreases during solar minimum, more cosmic rays penetrate to Earth. The cosmic ray intensity varies inversely with solar activity. This solar modulation affects mainly cosmic rays with energies below 10 billion electron volts. Higher energy cosmic rays ignore the solar wind completely and maintain constant intensity regardless of solar cycle phase. The Sun can only regulate its immediate neighborhood. The 11-year solar cycle creates 11-year cosmic ray cycles that scientists can measure with ground-based detectors. Cosmic ray intensity reaches maximum during solar minimum and minimum during solar maximum. This creates a cosmic ray weather pattern tied to solar behavior. This solar traffic control demonstrates how local stellar activity can influence cosmic ray environment even for particles that originated in distant parts of the galaxy. Earth's magnetic field acts like a cosmic ray bouncer that selectively admits particles based on their energy and electric charge. This magnetic filtering system is called the geomagnetic rigidity cutoff. Rigidity combines particle energy and charge into a single measure of magnetic resistance. Low rigidity cosmic rays get deflected away from Earth by our magnetic field. High rigidity cosmic rays punch through the magnetic barrier and reach our atmosphere. This creates a cosmic ray admission system based purely on particle properties. The rigidity cutoff varies with geographic location on Earth. Cosmic rays can penetrate most easily near the magnetic poles, where field lines point vertically downward. The magnetic equator provides the strongest cosmic ray shielding. Different elements experience different cutoff energies based on their electric charge. A carbon nucleus must carry 6 times more energy than a proton to penetrate the same magnetic barrier. This creates element-dependent cosmic ray admission criteria. Earth's magnetic gatekeeper system means that cosmic ray intensity and composition both depend on where you live on the planet and how Earth's magnetic field strength changes over time. Cosmic ray arrival directions create one of astronomy's greatest puzzles. Low and medium energy cosmic rays arrive at Earth from all directions with nearly perfect uniformity. This isotropy suggests that magnetic fields in space scramble cosmic ray directions during their galactic journey. However, the highest energy cosmic rays show slight but measurable deviations from perfect isotropy. These ultra-high energy particles appear to avoid coming from the direction of our galaxy's center. They also show weak correlations with certain types of nearby galaxies. This directional information provides the only way to identify cosmic ray sources directly. Lower energy cosmic rays have their directions completely scrambled by galactic magnetic fields. Only the highest energy particles maintain some memory of their original direction. The weak anisotropy at ultra-high energies suggests that these cosmic rays travel relatively short distances through space. Long-distance travel would completely erase directional information even for the most energetic particles. This cosmic direction puzzle reveals that the universe operates both local and distant cosmic ray accelerators, with only the most powerful local sources providing detectable directional signatures. A curious feature appears in the cosmic ray energy spectrum at certain altitudes in Earth's atmosphere. Secondary particles created by cosmic ray collisions sometimes carry more energy than expected. This creates a secondary maximum in cosmic ray intensity within the upper atmosphere. When high-energy cosmic rays hit atmospheric nuclei, they create cascades of secondary particles. Some of these secondary particles maintain high energies and create their own mini-cascades. This secondary particle multiplication can enhance cosmic ray intensity at specific atmospheric depths. The secondary maximum appears most prominently for certain types of secondary particles like muons. Muons are heavy electron-like particles created in cosmic ray showers. They can penetrate deep into the atmosphere while maintaining high energies. This atmospheric amplification zone affects cosmic ray measurements made by aircraft, balloons, and spacecraft at different altitudes. The secondary maximum can make cosmic ray intensity appear higher than expected at certain heights above Earth's surface. The secondary particle enhancement demonstrates how Earth's atmosphere actively participates in cosmic ray physics rather than simply absorbing cosmic particles passively. 60 miles above your head, cosmic warfare erupts every second in complete silence. A single high-energy cosmic ray particle slams into an air molecule with the force of a microscopic atomic bomb. This collision triggers an invisible explosion that creates billions of new particles within microseconds. Scientists call this phenomenon an air shower. Air shower means the cascade of secondary particles created when a cosmic ray hits Earth's atmosphere. The original cosmic particle gets destroyed in the collision, but its energy lives on in the shower of new particles racing toward Earth's surface. One cosmic ray impact can create a billion secondary particles that spread across several square miles. The shower particles rain down like invisible confetti from the cosmic explosion. Most shower particles reach ground level within a few millionths of a second after the initial collision. This atmospheric particle explosion happens about 10 times per second over every square meter of Earth's surface. The air above your head constantly sparkles with invisible atomic fireworks as cosmic rays collide with atmospheric molecules. The cosmic ray air shower represents the most common high-energy physics experiment in the universe, occurring billions of times per second throughout Earth's atmosphere. When a cosmic ray nucleus hits an atmospheric nucleus, the strong nuclear force takes control of the collision. Strong force is the powerful attraction that normally holds atomic nuclei together. During cosmic ray collisions, this force becomes a destructive demolition tool. The cosmic collision shatters both the incoming cosmic ray nucleus and the target air nucleus into smaller fragments. These nuclear fragments include protons, neutrons, and exotic particles called pions. Pions are unstable particles that exist only briefly before decaying into other particles. Each nuclear collision creates multiple new particles that race outward with high energies. These collision products then hit other atmospheric nuclei, creating more nuclear explosions in a growing chain reaction. The nuclear cascade multiplies exponentially as it propagates through the atmosphere. The nuclear cascade continues until the collision fragments lose too much energy to create more nuclear reactions. This typically happens after about 10 generations of collisions. By then, a single cosmic ray has triggered hundreds of nuclear explosions throughout the upper atmosphere. This nuclear demolition process transforms one incoming cosmic particle into a complex shower containing dozens of different particle types created through repeated nuclear destruction. Some particles from nuclear collisions are neutral pions that immediately decay into gamma rays. Gamma rays are extremely high-energy light particles that travel at light speed through the atmosphere. These invisible light bullets trigger their own type of particle creation process. When a gamma ray encounters the electric field around an atomic nucleus, something remarkable happens. The pure energy of the gamma ray converts directly into matter, but specifically an electron and a positron. This process is called pair production because it creates a particle pair from pure energy. The newly created electron and positron race through the atmosphere at nearly light speed. As they move, they radiate more gamma rays through interactions with air molecules. These secondary gamma rays then create more electron-positron pairs in an electromagnetic avalanche. This electromagnetic cascade grows exponentially until the particles lose too much energy to create more pairs. The cascade can contain millions of electrons, positrons, and gamma rays, all created from the energy of the original cosmic ray collision. The electromagnetic component represents the light-based portion of cosmic ray air showers, demonstrating Einstein's mass-energy equivalence on a cosmic scale throughout Earth's atmosphere. Not all air shower particles stop in the atmosphere. A special type of particle called a muon can penetrate all the way to Earth's surface and even deep underground. Muons are heavy cousins of electrons that behave like superpowered versions of ordinary electrons. Muons get created when charged pions from nuclear collisions decay during their brief lifetimes. Unlike electrons, muons can penetrate through enormous amounts of matter without getting absorbed. A muon can travel through miles of rock or water while maintaining most of its energy. Most cosmic ray particles that actually reach ground level and hit your body are muons from atmospheric showers. The original cosmic ray particle gets destroyed high in the atmosphere, but its muon descendants complete the journey to Earth's surface. Muons live only 2/millionths of a second before decaying into electrons and neutrinos. However, their high speeds cause time dilation effects predicted by Einstein's relativity. From the muon's perspective, time passes more slowly, allowing them to travel much farther than expected. This muon component provides the primary way that cosmic ray energy reaches Earth's surface, carrying the signature of high-altitude cosmic collisions down to ground level. Air shower particles moving through the atmosphere sometimes exceed the speed of light in air. This creates an impossible situation that nature resolves through spectacular light emission. The particles emit brilliant blue flashes, called Cherenkov radiation, as they violate the local speed limit. Light travels slower in air than in empty space because air molecules slow down light waves. High-energy particles from cosmic ray showers can move faster than this reduced light speed. When a particle moves faster than light in a medium, it creates a sonic boom made of light instead of sound. Cherenkov light appears as a brilliant blue glow that marks the path of ultra-fast particles through the atmosphere. This blue lightning provides a way to track air shower development visually. The intensity and direction of Cherenkov flashes reveal information about the original cosmic ray energy and direction. Special telescopes can detect these brief blue flashes during clear, dark nights. The Cherenkov light pulses last only a few billionths of a second, requiring extremely sensitive detection equipment to capture them. This faster-than-light phenomenon allows scientists to photograph cosmic ray air showers directly using the blue light signature created by speed of light violations. Air shower particles don't fall straight down like rain. Instead, they spread outward as they cascade through the atmosphere, creating an invisible umbrella of particles that can span several miles in diameter. This lateral spreading allows a single cosmic ray to trigger detectors separated by vast distances simultaneously. The particle spreading occurs because each collision in the shower imparts sideways momentum to the newly created particles. Multiple generations of collisions gradually spread the shower particles across increasingly large areas as they descend through the atmosphere. High-energy cosmic rays create the largest particle umbrellas. Ultra-high energy events can spread shower particles across areas larger than entire cities. Thousands of detection stations may record signals from a single cosmic ray impact within the same microsecond. The lateral distribution pattern reveals important information about the original cosmic ray. Light cosmic ray nuclei create narrow showers with steep particle distributions. Heavy nuclei create broad showers with gentle particle distributions across wider areas. This particle spreading effect allows scientists to build cosmic ray observatories that cover thousands of square kilometers using networks of individual detectors spaced miles apart. Air shower particle numbers don't increase forever as the shower develops. Instead, they reach a maximum at a specific atmospheric depth before declining toward ground level. Scientists call this peak the shower maximum, the atmospheric altitude where particle numbers reach their highest values. The shower maximum occurs when particle creation rates exactly balance particle absorption rates in the atmosphere. Above this altitude, particle numbers grow exponentially. Below this altitude, atmospheric absorption removes more particles than collisions create. Different cosmic ray elements create shower maxima at different atmospheric depths. Light elements like hydrogen create maxima high in the atmosphere. Heavy elements like iron create maxima deeper in the atmosphere. This difference allows scientists to identify cosmic ray composition. The shower maximum depth depends on atmospheric conditions like air density and temperature. Seasonal and daily atmospheric variations cause measurable changes in where shower maxima occur. Weather systems can affect cosmic ray detection through atmospheric density changes. This atmospheric sweet spot provides crucial information about cosmic ray properties by revealing where in the atmosphere each air shower reaches peak particle production. Air shower particles excite nitrogen molecules in Earth's atmosphere, causing them to emit ultraviolet light like cosmic neon signs. When high-energy particles collide with nitrogen, they boost electrons in nitrogen atoms to higher energy levels. These excited electrons quickly return to normal, releasing ultraviolet fluorescence light. This fluorescence process allows scientists to observe air shower development directly through the faint light emitted along the shower track. The ultraviolet glow traces the entire path of the particle cascade from the initial collision point down through the atmosphere. Fluorescence telescopes can observe cosmic ray air showers on clear, moonless nights by detecting this faint atmospheric glow. The light intensity reveals particle numbers at each altitude. The light track reveals the shower's three-dimensional development through the atmosphere. Each air shower creates a brief ultraviolet lightning bolt that streaks across dozens of miles of atmosphere within microseconds. This cosmic atmospheric advertising provides a complete record of how particle showers develop from start to finish. The nitrogen fluorescence technique allows scientists to measure cosmic ray properties by reading the atmospheric light signatures created when space particles collide with air molecules. Air shower particles carry electric charge as they race through Earth's magnetic field. Moving electric charges in magnetic fields emit radio waves, the same principle that makes radio antennas work. Cosmic ray air showers thus become natural radio transmitters, broadcasting their presence across the electromagnetic spectrum. The radio emission occurs because Earth's magnetic field deflects the charged particles in air showers. Electrons and positrons get bent in opposite directions, creating charge separation that oscillates as the shower develops. This oscillating charge distribution radiates radio waves like a cosmic antenna array. radio telescopes can detect these cosmic ray radio signals even during daylight hours when optical methods fail. The radio technique works in all weather conditions and provides complementary information about air shower properties like energy and composition. The radio signals from air showers span frequencies from about 30 to 300 megahertz, the same range used for FM radio broadcasting. Each cosmic ray creates a brief radio burst lasting less than a millionth of a second. This radio thunder from cosmic ray showers demonstrates how moving electric charges naturally create electromagnetic radiation detectable by radio astronomy techniques. Scientists must work backwards from air shower measurements to determine what type of cosmic ray particle created each event. This cosmic detective work requires analyzing clues scattered across miles of ground to reconstruct the properties of particles that were destroyed 60 miles overhead. The core reconstruction process combines data from hundreds of detectors that record different aspects of each air shower. Particle arrival times reveal the shower's direction. Particle densities reveal the shower's energy. Particle types reveal the cosmic ray's composition. Computer simulations help scientists understand how different cosmic ray particles would create different air shower signatures. By comparing measured showers with simulated ones, researchers can identify which type of cosmic ray most likely caused each observed event. The reconstruction accuracy improves with detector coverage and shower energy. High-energy events create more particles over larger areas, providing more clues for the cosmic detective work. Low-energy events leave fewer traces and prove more difficult to analyze. This cosmic forensic science allows researchers to study cosmic ray particles that were destroyed during atmospheric entry by analyzing the evidence they left behind in their particle showers. Every cosmic ray hid inside your body performs microscopic surgery on your genetic material. DNA is the twisted ladder-shaped molecule that contains all genetic instructions for life. When high-energy cosmic particles crash into DNA, they cut through the molecular bonds like invisible atomic scalpels. These cosmic scalpels can cut DNA in two different ways. Direct hits break the DNA backbone immediately through sheer impact force. Indirect hits create harmful chemicals called free radicals that attack DNA from the inside. Free radicals are unstable molecules that steal electrons from DNA and damage its structure. A single cosmic ray particle can break both strands of the DNA double helix simultaneously. This creates a double-strand break, the most dangerous type of DNA damage possible. Cells have repair mechanisms, but double-strand breaks often overwhelm these natural repair systems. Most DNA damage occurs in cells that aren't actively dividing. However, cosmic rays also hit rapidly dividing cells like those in bone marrow, intestines, and reproductive organs. These hits can cause mutations that get passed to daughter cells during cell division. This cosmic molecular surgery operates continuously throughout your body, creating thousands of DNA breaks every day through the constant bombardment of space radiation. Commercial aircraft cruise at altitudes where Earth's atmospheric shielding becomes much thinner. At 35,000 feet, the atmosphere blocks far fewer cosmic rays than at ground level. Flight crews working at these altitudes receive cosmic ray doses 100 times higher than people living at sea level. Airline pilots and flight attendants accumulate more radiation exposure than many nuclear plant workers. A typical pilot flying international routes receives about 5 millisieverts of cosmic radiation per year. This exceeds the annual dose limit for pregnant radiation workers in many countries. The cosmic ray dose increases dramatically with altitude and latitude. Flights over polar routes experience the highest cosmic radiation because Earth's magnetic field provides less protection near the poles. Transpolar flights from New York to Tokyo expose passengers to cosmic ray doses equivalent to several chest X-rays. Frequent flyers who take multiple international flights per month can accumulate significant cosmic ray doses over their lifetimes. Business travelers flying 100,000 miles per year receive cosmic radiation equivalent to living next to a nuclear power plant. The aviation industry represents the largest occupational group exposed to cosmic radiation, with hundreds of thousands of flight crew members receiving elevated cosmic ray doses throughout their careers. Beyond Earth's magnetic field, astronauts enter a cosmic radiation battlefield where space itself becomes hostile to human biology. The Apollo astronauts reported seeing bright flashes even with their eyes closed during lunar missions. These flashes were cosmic ray particles hitting their optic nerves directly. Astronauts on the International Space Station receive cosmic ray doses about 10 times higher than airline crews. During their 6-month missions, they accumulate radiation exposure equivalent to thousands of medical X-rays. This cosmic bombardment increases their lifetime cancer risk significantly. Solar particle events create the greatest radiation danger for astronauts. When the sun launches massive particle storms, astronauts must take shelter in the most heavily shielded parts of their spacecraft. These solar storms can deliver lethal radiation doses within hours. Future missions to Mars will expose astronauts to cosmic radiation for years without Earth's magnetic protection. The round trip to Mars could expose astronauts to cosmic ray doses approaching the limits of acceptable lifetime cancer risk. Space agencies now consider cosmic radiation the primary obstacle to long-duration human space missions, requiring new shielding technologies and medical countermeasures to protect astronaut health. Modern electronics face constant attack from individual cosmic ray particles. A single high-energy cosmic ray can flip bits in computer memory, causing software crashes and data corruption. This phenomenon is called a single event upset. When one particle disrupts an entire electronic system, cosmic ray hits on microprocessors can cause calculators to display wrong answers, smartphones to freeze, and aircraft navigation systems to malfunction. The electronics industry spends billions of dollars annually protecting sensitive systems from cosmic ray interference through radiation-hardened designs. Satellites experience thousands of single-event upsets per year from cosmic ray bombardment. Each cosmic ray hit can corrupt data storage, reset computer processors, or trigger false commands. Some satellite failures result directly from cosmic ray damage to critical electronic components. The miniaturization of electronics makes cosmic ray interference worse. Smaller transistors require fewer electrons to switch between on and off states. A single cosmic ray can now disrupt multiple transistors simultaneously in advanced microprocessors. Modern society's dependence on electronics means that cosmic ray single-event upsets affect everything from bank transactions to medical equipment, making space radiation an increasing threat to technological civilization. Cosmic rays have been mutating DNA throughout Earth's entire biological history. These cosmic mutations provide the raw material for natural selection and evolutionary change. Without cosmic ray mutagenesis, evolution would proceed much more slowly and life might never have achieved its current diversity. Cosmic radiation creates about 10% of all natural background mutations in living organisms. Over millions of generations, these cosmic mutations accumulate into significant evolutionary changes. Some mutations prove harmful and get eliminated by natural selection. Others provide advantages that help organisms survive and reproduce. The cosmic mutation rate remains relatively constant across geological time. This provides a steady supply of genetic variation that natural selection can act upon. Cosmic rays thus function as evolution's random number generator, creating the genetic lottery that drives biological innovation. Many beneficial mutations throughout evolutionary history may have originated from cosmic ray impacts. The mutations that allowed mammals to develop larger brains, birds to develop flight, or plants to develop photosynthesis could have started with cosmic ray DNA damage. This cosmic evolutionary engine has been operating for billions of years, helping to create the incredible diversity of life forms on Earth through constant genetic experimentation driven by space radiation. Earth's atmosphere acts like a giant suit of armor that absorbs most cosmic ray particles before they reach the surface. The atmosphere contains enough material to stop all but the most energetic cosmic rays. This atmospheric armor provides crucial protection for surface-dwelling life. The atmosphere stops cosmic rays through a process called nuclear attenuation. Nuclear attenuation means that cosmic ray nuclei get absorbed or broken apart when they collide with air molecules. Each collision removes energy from the cosmic ray or destroys it completely. The atmospheric armor works best against lower-energy cosmic rays and becomes less effective against ultra-high energy particles. About 90% of galactic cosmic rays get absorbed in the upper atmosphere before reaching ground level. Only the highest energy cosmic rays can penetrate through the entire atmospheric shield. Without atmospheric protection, Earth's surface would receive cosmic ray doses lethal to most current life forms. The atmospheric armor reduces surface cosmic ray intensity by about 100 times compared to what organisms would experience in space. This atmospheric shielding system has protected surface life throughout Earth's history, allowing complex organisms to evolve and thrive under the cosmic ray protection provided by our planet's air ocean. Earth generates a magnetic force field that extends thousands of miles into space. This magnetosphere acts like an invisible shield that deflects many cosmic ray particles before they can reach our atmosphere. The magnetic protection works best against lower-energy cosmic rays with modest speeds. Charged particles from space get trapped in Earth's magnetic field lines and spiral around them instead of hitting the atmosphere directly. Many cosmic rays get deflected completely away from Earth or channeled toward the magnetic poles, where they create aurora displays. The magnetosphere's protective strength varies with location on Earth. People living near the magnetic equator receive better cosmic ray protection than those living near the magnetic poles. The magnetic field also fluctuates in strength, providing variable protection over time. Solar storms can temporarily compress Earth's magnetosphere and reduce its protective effectiveness. During major magnetic storms, more cosmic rays penetrate to lower altitudes in the atmosphere. These events can increase radiation exposure for airline passengers and crew. Without this magnetic shield, Earth would receive much higher cosmic ray doses that could make surface life difficult or impossible. The magnetosphere represents one of the key protective systems that makes our planet habitable. Cosmic ray particles create chemical reactions in Earth's atmosphere that affect the ozone layer. When cosmic rays hit nitrogen and oxygen molecules in the upper atmosphere, they create nitrogen oxides, chemicals that can destroy ozone molecules. The ozone layer protects surface life from harmful ultraviolet radiation. This cosmic chemistry laboratory operates continuously throughout the upper atmosphere. Cosmic ray interactions produce about 10% of the nitrogen oxides that naturally destroy atmospheric ozone. These cosmic ray effects represent a natural ozone depletion mechanism that has operated throughout Earth's history. The cosmic ray ozone chemistry varies with solar activity and cosmic ray intensity. During periods of low solar activity, more cosmic rays reach Earth's atmosphere and create more ozone-destroying chemicals. This creates a natural cycle of ozone depletion and recovery linked to cosmic ray variations. High-energy cosmic ray events can create temporary ozone holes in the upper atmosphere. Major cosmic ray increases can reduce ozone levels by several percent for months or years. These cosmic ozone effects may influence surface ultraviolet radiation levels and climate patterns. The Cosmic Ray Ozone Laboratory demonstrates how space radiation influences Earth's atmospheric chemistry and potentially affects the protective ozone shield that guards surface life from dangerous solar ultraviolet radiation. Cosmic ray particles may influence Earth's weather by providing nucleation sites for cloud formation. When cosmic rays hit the lower atmosphere, they create ions, electrically charged atoms and molecules. These ions can help water vapor condense into cloud droplets under certain atmospheric conditions. The cosmic ray cloud seeding hypothesis suggests that changes in cosmic ray intensity could affect cloud cover and climate. More cosmic rays would create more ions and potentially more low-altitude clouds. These additional clouds could reflect more sunlight and cool Earth's climate. The relationship between cosmic rays and clouds remains scientifically controversial. Some studies find correlations between cosmic ray intensity and low-altitude cloud cover. Other studies find no significant relationship. The cosmic ray climate connection requires more research to establish definitively. Solar activity affects cosmic ray intensity through the 11-year solar cycle. During solar minimum, more cosmic rays reach Earth and could potentially increase cloud formation. During solar maximum, fewer cosmic rays reach Earth and cloud formation might decrease. This cosmic weather modification system could represent another way that space radiation influences Earth's environment, potentially affecting global climate patterns through cosmic ray control of atmospheric cloud formation processes. People living at high altitudes receive higher cosmic ray doses and show small increases in certain cancer rates. The thinner atmosphere at high elevations provides less cosmic ray shielding. Residents of cities like Denver, Colorado, experience about twice the cosmic ray exposure of people living at sea level. Studies of high-altitude populations reveal small but measurable increases in some cancer types. Cosmic ray exposure appears to contribute a few percent to overall cancer risk in mountain communities. However, high-altitude residents often have lower overall cancer rates due to other lifestyle and environmental factors. The cosmic ray cancer risk becomes more significant for people with high cumulative exposures. Airline crew members who spend careers at high altitudes show slightly elevated rates of certain cancers, including breast cancer and skin cancer. The increased risk remains relatively small compared to other cancer risk factors. Cosmic ray cancer risk varies by geographic location due to Earth's magnetic field geometry. People living at high latitudes near the magnetic poles receive higher cosmic ray doses than those living near the magnetic equator. This creates geographic variations in cosmic ray cancer risk. This natural cosmic ray cancer calculator demonstrates that space radiation contributes to human disease risk, though the contribution remains small compared to other environmental and lifestyle cancer risk factors. Some scientists propose that low-level cosmic radiation exposure might actually benefit human health through a process called radiation hormesis. Hormesis means that small amounts of a harmful substance can trigger beneficial biological responses that improve overall health and resistance to disease. The hormesis hypothesis suggests that constant low-level cosmic ray exposure might stimulate DNA repair mechanisms, boost immune system function, and increase cellular resistance to future radiation damage. This biological stress response could make organisms more resilient to various health challenges. Studies of populations with naturally high background radiation show mixed results regarding hormesis effects. Some high radiation areas show lower cancer rates than expected, while others show higher rates. The radiation hormesis debate continues among radiation biologists and health physicists. Laboratory studies with animals exposed to low-level radiation sometimes show beneficial effects, including increased longevity, improved immune function, and enhanced resistance to subsequent high-dose radiation exposure. However, these results don't always translate to human populations. The cosmic ray hormesis question represents one of the most intriguing aspects of space radiation biology. The possibility that the cosmic bombardment that has bathed Earth throughout its history might actually help rather than harm the organisms that evolved under its constant influence. How do you catch something you cannot see, touch, or hear? Scientists solve this cosmic detective problem by building vast networks of particle sensors spread across enormous areas. These ground-based detectors work like cosmic burglar alarms that trigger whenever invisible cosmic ray showers hit Earth's surface. Each detection station contains scintillator materials that flash with light when cosmic ray particles pass through them. Scintillators are special plastics or crystals that convert invisible particle energy into visible light flashes. These brief light pulses get detected by sensitive photodetectors and converted into electrical signals. Thousands of these cosmic burglar alarms cover areas spanning hundreds or thousands of square miles. When a cosmic ray creates an air shower, particles hit multiple detector stations simultaneously. The network records the exact timing and intensity of particle hits across the entire area. This synchronized detection allows scientists to triangulate the cosmic ray's original direction and estimate its energy. The more detectors that record simultaneous hits, the more accurately researchers can reconstruct the invisible cosmic event that occurred miles overhead. The ground-based surveillance network represents the most common method for hunting cosmic ray particles across vast areas using coordinated arrays of sensitive light-producing materials. Why would scientists point telescopes at empty sky instead of stars and galaxies? These specialized fluorescence telescopes hunt for the faint ultraviolet glow that cosmic ray air showers create in Earth's atmosphere. The telescopes work like cosmic lightning detectors searching for brief flashes in the dark. When cosmic ray particles crash through the atmosphere, they excite nitrogen molecules that emit ultraviolet fluorescence light. This atmospheric glow traces the entire path of the particle shower from 60 miles altitude down to ground level. The fluorescence creates a brief cosmic lightning bolt spanning dozens of miles. Giant segmented mirrors collect this faint atmospheric light and focus it onto sensitive cameras. The telescopes operate only during clear, moonless nights when the sky is dark enough to detect the subtle nitrogen glow. Even city lights can overwhelm these delicate light signals. Each fluorescence flash lasts only a few millionths of a second. The telescope cameras must capture these brief cosmic events in real time as they streak across the sky. Computer systems analyze the light intensity and track length to determine cosmic ray properties. This atmospheric light hunting technique allows scientists to observe cosmic ray air shower development directly by reading the fluorescent signatures written across Earth's upper atmosphere. Can you detect invisible particles by watching for blue light underwater? Cherenkov detectors use this exact principle by suspending light sensors inside enormous tanks filled with pure water. These underwater light traps catch the blue flashes created when cosmic ray particles move faster than light in water. High-speed particles entering the water tanks emit brilliant blue Cherenkov radiation cones. This blue light appears when particles exceed light speed in water, which is slower than light's speed in empty space. The blue light cone points in the direction the particle was traveling. Arrays of photodetectors line the water tank walls to catch these brief blue flashes from all angles. The timing and intensity of light hits on different detectors reveals the particle's path, energy, and type. Multiple particles create complex light patterns that computers analyze to reconstruct the original cosmic event. The largest Cherenkov detectors contain millions of gallons of ultra-pure water in underground chambers. These buried water tanks shield the detectors from surface contamination while remaining sensitive to cosmic ray particles penetrating from above. This underwater blue light hunting method provides precise measurements of cosmic ray particle directions and energies through the detection of faster than light Cherenkov radiation signatures. At what altitude do cosmic ray particles arrive before Earth's atmosphere destroys them? High-altitude balloon experiments carry particle detectors to the stratosphere, where they can intercept cosmic rays directly before atmospheric collisions corrupt the original particle properties. Scientific balloons inflate to the size of football stadiums and carry detector payloads to altitudes of 130,000 feet above sea level. At these heights, the atmosphere becomes so thin that cosmic ray particles can reach detection equipment without suffering major energy losses. These stratospheric spy missions operate for days or weeks before parachuting their precious data back to Earth. The balloon-borne detectors record cosmic ray composition, energy, and arrival directions with much better precision than ground-based instruments. Balloon experiments revealed many fundamental cosmic ray properties, including the precise mix of elements and the detailed energy spectrum. These high-altitude reconnaissance missions bridge the gap between ground-based observations and space-based measurements. The stratospheric balloon platform provides the most cost-effective method for intercepting cosmic ray particles in their nearly pristine state before atmospheric interactions alter their original characteristics. Where can scientists study cosmic rays without any interference from Earth's magnetic field or atmosphere? Space-based detectors launched aboard robotic spacecraft provide the only way to measure cosmic ray particles in their completely natural state throughout interplanetary space. These cosmic reconnaissance missions carry sophisticated particle analyzers beyond Earth's magnetosphere, where cosmic rays flow freely. The spacecraft instruments can identify individual cosmic ray nuclei and measure their precise energies without atmospheric contamination. Voyager 1 and 2 spacecraft continue measuring cosmic rays after 40 years in space as they travel through the boundary between our solar system and interstellar space. These robot ambassadors discovered how solar wind affects cosmic ray propagation throughout our local galactic neighborhood. Other interplanetary missions study cosmic ray variations with solar activity, galactic position, and distance from Earth. These space-based measurements provide ground truth data for understanding cosmic ray behavior throughout the solar system. The robotic space probe platform offers the gold standard for cosmic ray research by measuring particles in their unmodified state far from any planetary magnetic or atmospheric interference. Can you build a cosmic ray detector larger than some entire countries? The Pierre Auger Observatory spans 3,000 square kilometers of Argentine grassland with 1,600 individual detection stations monitoring the sky for ultra-high-energy cosmic ray events. This continental-scale observatory hunts for the rarest and most energetic cosmic ray particles in the universe. Ultra-high-energy cosmic rays strike Earth so infrequently that detecting them requires enormous collection areas. The Auger Observatory operates like a cosmic fishing net cast across an area larger than Rhode Island. Each detection station sits 1.5 kilometers from its neighbors in a triangular grid pattern across the Argentine countryside. When an ultra-high-energy cosmic ray creates a massive air shower, particles trigger dozens of detector stations simultaneously across hundreds of square kilometers. The observatory combines ground-based particle detectors with fluorescence telescopes to provide complementary measurements of the same cosmic events. This hybrid approach yields the most complete pictures of ultra-high-energy cosmic ray properties available anywhere. The Pierre Auger Observatory represents the largest scientific instrument ever built and the most sensitive detector for the universe's most powerful cosmic ray particles. Why would anyone build a particle detector inside Antarctic ice? The IceCube Observatory transforms a cubic kilometer of South Pole ice into the world's largest neutrino telescope. This frozen detector hunts for cosmic neutrinos, ghostly particles that cosmic ray interactions create throughout the universe. Scientists lowered 5,160 light sensors deep into Antarctic ice through holes melted by hot water drilling. These photodetectors wait frozen in darkness for the rare blue flashes that neutrinos create when they finally interact with ice molecules. Cosmic ray interactions in distant galaxies produce neutrinos that travel billions of light years through space without obstruction. When these cosmic messengers finally hit Earth, most pass straight through the planet without stopping. Only 1 in a trillion neutrinos interacts with matter and produces detectable light. The IceCube Ice Laboratory also detects high-energy muons created by cosmic ray air showers in the atmosphere above Antarctica. These muon measurements complement the neutrino detections to provide multiple perspectives on cosmic ray sources. This Antarctic ice hunting ground demonstrates how scientists can transform natural environments into enormous particle detectors for studying the universe's most elusive cosmic particles. Could cosmic ray antimatter provide evidence for dark matter particles? The Piamula satellite carries sophisticated instruments designed to hunt for antimatter particles among the cosmic ray population. These antimatter signatures might reveal dark matter particle collisions occurring throughout our galaxy. Pamel orbits Earth with a magnetic spectrometer that bends charged particle paths to separate matter from antimatter. The satellite measures precise cosmic ray composition, including the rare antimatter particles that standard astrophysical processes cannot easily explain. The antimatter hunting mission discovered unexpected excesses of positrons, antimatter electrons, in the cosmic ray population. These positron anomalies could indicate dark matter particle annihilation or exotic astrophysical acceleration processes. Antimatter cosmic rays arrive in such small quantities that detecting them requires years of careful measurements with extremely sensitive instruments. PMLA accumulated data for over a decade to build statistically significant antimatter detection records. This orbital antimatter surveillance demonstrates how cosmic ray composition measurements can probe fundamental physics questions about dark matter and exotic particle interactions throughout the universe. How can scientists analyze cosmic ray composition with laboratory precision in the hostile environment of space? The Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station uses powerful magnets to sort cosmic particles by their electric charge and momentum like a cosmic coin counting machine. AMS-02 contains a superconducting magnet that creates magnetic fields 4,000 times stronger than Earth's magnetic field. This powerful magnet bends cosmic ray particle paths according to their charge and energy. Different particle types follow different curved trajectories through the magnetic field. The Space Station Laboratory measures cosmic ray particles with unprecedented precision using multiple detector layers that track each particle's path through the magnetic field. These measurements reveal particle identity, energy, and charge with accuracy approaching terrestrial laboratory standards. Over 10 years of operation, AMS-02 has analyzed over 100 billion cosmic ray particles to create the most detailed cosmic ray composition measurements ever achieved. The space station platform provides stable, long-term operation impossible with balloon or satellite missions. This orbital magnetic laboratory represents the most sophisticated cosmic ray analysis facility ever deployed in space, combining powerful magnetic fields with precision tracking detectors. What does a cosmic ray sound like on a radio? Radio detection arrays use hundreds of antennas to listen for the electromagnetic signals that cosmic ray air showers broadcast as they develop through Earth's atmosphere. These radio ears detect cosmic ray thunder across frequencies used for FM radio broadcasting. When cosmic ray particles cascade through the atmosphere, the moving electric charges emit radio waves like natural radio transmitters. These cosmic radio bursts last less than a millionth of a second, but can be detected by radio telescopes even during daylight hours. Radio detection works in all weather conditions, unlike optical techniques that require clear skies. The radio signals provide information about cosmic ray energy and composition through the characteristics of the electromagnetic pulse each air shower creates. Arrays of simple radio antennas spread across large areas can detect cosmic ray radio signals much more cheaply than traditional particle detectors. This makes radio detection attractive for covering enormous areas with limited budgets. The radio ear approach represents an emerging technique that could revolutionize cosmic ray detection by using the natural electromagnetic signatures that particle showers broadcast during atmospheric development. How can computers learn to recognize cosmic ray signatures better than human experts? Machine learning algorithms analyze millions of cosmic ray air shower patterns to automatically classify particle types and energies. These artificial intelligence detectives never get tired and can process data much faster than human researchers. Complex cosmic ray events create intricate patterns of particle hits across detector arrays. Traditional analysis requires experts to manually interpret these patterns to determine cosmic ray properties. Machine learning automates this pattern recognition process using computer algorithms trained on known cosmic ray examples. Neural networks and deep learning systems can identify subtle signatures in cosmic ray data that human analysts might miss. These AI systems improve their performance continuously as they analyze more cosmic ray events and learn new pattern recognition strategies. The artificial intelligence approach becomes essential for handling the enormous data volumes that modern cosmic ray observatories generate. Some experiments record millions of cosmic ray events annually, far too many for human analysis. These AI pattern recognition systems represent the future of cosmic ray research, where machine learning algorithms will automatically classify and analyze cosmic events faster and more accurately than traditional human-based methods. Why do cosmic ray researchers obsess over timing measurements accurate to billionths of a second? Ultra-precise timing allows scientists to reconstruct the exact three-dimensional path that invisible cosmic ray showers follow through Earth's atmosphere. These cosmic stopwatch networks track particle shower fronts with nanosecond precision. When cosmic ray particles hit detector stations spread across large areas, the arrival time differences reveal the shower's direction and development. Light travels about 1 foot per nanosecond, so timing precision of billionths of a second allows position measurements with foot-level accuracy. GPS satellite signals provide the master timing reference that synchronizes cosmic ray detector networks worldwide. Each detector station contains atomic clock precision timing systems that record particle arrival times referenced to universal coordinated time. The nanosecond timing precision allows researchers to track how cosmic ray shower fronts propagate across detector arrays and reconstruct the original cosmic ray direction to within 1 degree accuracy. This timing information proves crucial for identifying cosmic ray source locations. This cosmic chronometry network demonstrates how ultra-precise time measurements can reveal the detailed geometry of invisible particle cascades developing at light speed throughout Earth's atmosphere. Cosmic ray particles act like cosmic breadcrumbs that reveal the invisible magnetic field structure throughout our galaxy. As these charged particles travel through space, galactic magnetic fields bend their paths like invisible highways guiding traffic flow. Scientists can reverse engineer these particle paths to create three-dimensional maps of magnetic fields spanning the entire Milky Way. Magnetic fields in space work like cosmic traffic controllers that deflect moving electric charges. Cosmic ray particles follow curved trajectories determined by magnetic field strength and direction. By analyzing cosmic ray arrival patterns at Earth, researchers can trace these magnetic highways backward through thousands of light years of space. Different cosmic ray energies experience different amounts of magnetic deflection. Low-energy particles get bent dramatically by weak magnetic fields. High-energy particles plow through strong magnetic fields with minimal deflection. This energy-dependent bending creates a cosmic triangulation system for mapping galactic magnetism. The cosmic ray magnetic mapping reveals that our galaxy contains organized magnetic field structures spanning thousands of light years. These galactic magnetic highways channel cosmic ray flow throughout the Milky Way and influence how particles propagate from their acceleration sites to Earth. This invisible GPS network demonstrates how cosmic ray particles serve as magnetic field tracers that reveal the hidden electromagnetic architecture organizing our entire galaxy. Interstellar space seems empty, but actually contains thin gas that cosmic ray particles must navigate during their million-year journeys. This interstellar medium acts like a cosmic obstacle course that gradually absorbs cosmic ray energy through countless tiny collisions. The gas density determines which cosmic rays survive their trek across the galaxy. Cosmic rays constantly collide with hydrogen and helium atoms floating between stars. Each collision removes a small amount of energy from the cosmic ray particle. After millions of collisions over millions of years, cosmic rays lose significant energy or get absorbed completely by the interstellar medium. The collision rate depends on interstellar gas density along different galactic routes. Dense molecular clouds absorb cosmic rays rapidly. Sparse regions between spiral arms allow cosmic rays to travel much farther without major energy loss. This creates cosmic ray shadows and bright zones throughout the galaxy. By measuring cosmic ray composition and energy spectra at Earth, scientists can estimate interstellar medium density along different galactic directions. Cosmic rays essentially serve as cosmic probes that sample gas conditions throughout their travel paths. This cosmic collision analysis reveals the detailed distribution of invisible interstellar matter that fills the apparently empty space between stars throughout our galaxy. Cosmic ray composition tells the story of stellar evolution throughout our galaxy's history. Different types of stars create different elements through nuclear fusion and explosive death. The mix of elements in cosmic rays reflects which stellar populations contributed most to cosmic ray acceleration over billions of years. Massive stars burn through their nuclear fuel quickly and explode as supernovas within 10 million years of formation. These stellar explosions create cosmic rays rich in oxygen, neon, and silicon elements forged in massive stellar cores. The abundance of these elements in cosmic rays reveals the rate of massive star formation throughout galactic history. Lower mass stars live much longer and contribute different elements to the galactic mix through stellar winds and planetary nebula formation. The cosmic ray element ratios reflect the relative contributions of fast-evolving massive stars versus slow-evolving lower-mass stars. Changes in cosmic ray composition over time would reveal how our galaxy's star formation rate varied throughout its 10 billion-year history. However, cosmic rays take millions of years to travel from their sources to Earth, so current measurements represent average conditions over recent galactic history. This stellar chemical archaeology allows scientists to study galactic evolution by reading the elemental signatures written in cosmic ray particles arriving from throughout the Milky Way. Could cosmic ray measurements solve one of the universe's greatest mysteries? Dark matter comprises 85% of all matter in the universe, yet no one knows what it actually is. Scientists search cosmic rays for antimatter signatures that might reveal dark matter particle interactions occurring throughout our galaxy. Dark matter particles might occasionally collide with each other and annihilate, creating bursts of normal matter and antimatter particles. These dark matter collision products would appear as excess antimatter in the cosmic ray population. Finding unexplained antimatter cosmic rays could provide the first direct evidence of dark matter interactions. Cosmic ray detectors have discovered mysterious excesses of antimatter particles that standard astrophysical processes cannot easily explain. These antimatter anomalies might indicate dark matter annihilation occurring throughout our galactic neighborhood. However, exotic astrophysical sources could also create antimatter cosmic rays. The dark matter hunt requires extremely precise measurements of cosmic ray antimatter ratios. Antimatter particles arrive mixed with billions of normal matter particles, making detection extremely challenging. Scientists need years of data collection to build statistically significant antimatter detection records. This cosmic antimatter detective work represents one of the most promising approaches for identifying dark matter through its potential signatures hidden within the cosmic ray particle population. Ultra-high-energy cosmic rays carry energies that dwarf anything humans can create in terrestrial laboratories. These cosmic particles reveal extreme acceleration processes operating throughout the universe under conditions impossible to reproduce on Earth. Nature operates cosmic accelerators millions of times more powerful than the largest human-built machines. The most energetic cosmic ray ever detected carried energy equivalent to a baseball thrown at 100 miles per hour, all contained within a single atomic nucleus. This represents 100 million times more energy than the most powerful human particle accelerators can achieve. Such extreme energies require acceleration mechanisms beyond current technological capabilities. These ultra-high-energy cosmic rays provide unique opportunities to study fundamental physics under conditions that cannot be created in Earth-based laboratories. The particles carry energies high enough to probe physics beyond the standard model of particle physics. By studying cosmic ray interactions at these extreme energies, scientists can investigate whether new physics phenomena emerge at energy scales inaccessible to human technology. These natural experiments occur continuously throughout the universe and deliver their results directly to Earth. This extreme physics research program demonstrates how cosmic ray astronomy allows scientists to study fundamental physics using the universe's natural particle accelerators as experimental apparatus. Cosmic ray particles travel so fast that they experience dramatic time dilation effects predicted by Einstein's special theory of relativity. These relativistic cosmic clocks provide continuous real-world tests of Einstein's predictions about how time behaves for objects moving at nearly light speed. Unstable particles called muons normally decay within 2 millionths of a second after creation. However, muons created in cosmic ray air showers travel at speeds so close to light speed that time passes more slowly from their perspective. This time dilation allows muons to survive much longer than expected and reach Earth's surface. Without relativistic time dilation, these high-speed muons would decay in the upper atmosphere and never reach ground level. The fact that cosmic ray muons regularly penetrate to Earth's surface provides direct observational confirmation of Einstein's time dilation predictions. Different cosmic ray particles moving at different speeds experience different amounts of time dilation. This creates a natural laboratory for testing relativistic effects across a wide range of velocities approaching light speed. These cosmic relativistic experiments occur millions of times per second throughout Earth's atmosphere, providing continuous verification of special relativity using naturally occurring high-speed particles. Our solar system currently travels through a region of space called the local hot bubble. This cosmic hot tub was carved out by multiple supernova explosions that occurred millions of years ago in our galactic neighborhood. The bubble's properties significantly influence which cosmic rays can reach our solar system. The local hot bubble contains hot, thin gas heated to millions of degrees by ancient stellar explosions. This hot bubble extends about 300 light-years in all directions from our solar system. The bubble's low gas density and hot temperature affect cosmic ray propagation through our local galactic region. Low-energy cosmic rays experience enhanced propagation through the local hot bubble because the thin gas provides fewer obstacles to particle motion. However, the bubble's magnetic field structure may deflect some cosmic rays around our local region. These competing effects influence the cosmic ray environment at Earth. Our solar system has been traveling through this cosmic hot tub for several million years. As we eventually exit the bubble and enter denser interstellar regions, the cosmic ray environment at Earth may change significantly over astronomical timescales. This local galactic environment demonstrates how our solar system's position within larger galactic structures influences the cosmic ray bombardment that Earth receives from throughout the galaxy. At specific cosmic ray energies, control of the cosmic particle population transitions from galactic sources to extragalactic ones. This cosmic border crossing occurs around 10 to the 18th power electron volts, an energy level where our galaxy's cosmic ray accelerators reach their limits and distant galaxy sources begin contributing more particles. Below this energy threshold, cosmic rays originate mainly from supernova remnants and other acceleration sites within our Milky Way galaxy. Above this threshold, cosmic rays increasingly come from active galactic nuclei, galaxy cluster shocks, and other extragalactic acceleration mechanisms operating outside our local galaxy. This galactic-extragalactic transition reveals itself through changes in cosmic ray composition, energy spectrum, and arrival directions. Galactic cosmic rays show signatures of local stellar environments. Extragalactic cosmic rays reflect acceleration processes in different types of galaxies and cosmic environments. The transition energy marks the maximum cosmic ray energy that our galaxy's magnetic fields can contain. Higher energy particles escape from the Milky Way and travel throughout intergalactic space. Lower energy particles remain trapped within our galaxy for millions of years. This cosmic shift change demonstrates how cosmic ray astronomy probes acceleration mechanisms operating across vastly different scales, from local galactic processes to universe-wide phenomena. The universe operates thousands of natural particle accelerators that achieve energies and conditions impossible to create with human technology. These cosmic acceleration sites represent natural laboratories for studying extreme physics processes under conditions that dwarf any terrestrial experimental facility. Supernova remnant shock waves accelerate particles across regions spanning dozens of light-years for thousands of years. Galaxy cluster merger shocks operate across millions of light-years for hundreds of millions of years. Active galactic nucleus jets accelerate particles along beams extending across multiple galaxies. These natural accelerators achieve particle energies millions or billions of times higher than the most powerful human-built machines. They operate under magnetic field strengths, radiation environments, and spatial scales completely beyond human technological capabilities. By studying cosmic ray particles from these natural accelerators, scientists can investigate physics processes occurring under the most extreme conditions in the universe. These cosmic laboratories provide experimental data about matter and energy behavior under conditions that cannot be reproduced on Earth. The universe thus provides a vast experimental physics program operating continuously across cosmic scales, delivering research results directly to Earth through cosmic ray particle bombardment. Understanding cosmic radiation becomes crucial for protecting human astronauts during long-duration space missions beyond Earth's magnetic protection. Future missions to Mars, asteroids, and outer planets will expose crews to cosmic ray bombardment for months or years without planetary magnetic shielding. Current cosmic ray research provides essential data for developing spacecraft shielding technologies and medical countermeasures. Scientists must predict cosmic ray dose rates throughout the solar system and design protection systems that keep astronaut radiation exposure within acceptable health limits. Solar activity predictions become critical for mission planning because solar particle events can create lethal radiation environments within hours. Cosmic ray monitoring systems will need to provide early warning of dangerous radiation storms that could threaten astronaut survival. Advanced spacecraft designs may use magnetic shields water barriers, or underground habitat modules to protect crews from cosmic radiation. However, these protection systems add significant mass and complexity to spacecraft, requiring careful engineering trade-offs between safety and mission practicality. This cosmic ray protection program represents one of the most important practical applications of cosmic ray research, enabling human exploration of the solar system by understanding and mitigating the radiation environment that space travelers will face.